So to get to our material today, this is the picture today. I think probably arguably the most iconic image of our planet. I'm sure you have all seen this many, many times. You might not know what it's from. It's actually Apollo 17. One of the Apollo astronauts took the picture on the way back to Earth after Apollo 17 landed on the moon. The reason I always think this picture is also interesting is because he actually took the picture upside down. But then, of course, because we are very north is up in our view of the world, they flip it around in this iconic image. So, perspective is always one of these things you have to keep in mind. And it should also be mentioned that the astronaut who took this, he always said that he really wished that he could drag the politicians up to look at the Earth and then realize that most of the things we fight about don't matter. So, something to think about as well. So today, what are we going to do? The age of the solar system. We're going to talk about how we know how old the Earth and all the other planets are. We're going to discuss various cosmic influences on Earth. Well, maybe not the activity. We might just be doing that Wednesday. Structure of the Earth's crust, changing crusts, and the Earth's interior are general things. So first, how old is the solar system and how do we know this? So there's something that I'm sure you have all heard of in some sort of capacity called radioactive decay. So if you have the nucleus of one type of atom, over time, it can change into the nucleus of another type of atom. Typically, radioactive decay you most talk about in terms of nuclear weapons or nuclear reactors or decay that happens in a very rapid period of time. But most radioactive decay that happens takes place over millions or even billions of years that happens in the universe. And this is just a natural process that happens over time to elements. So for example, if we have a neutron, and over time, there's a process called beta decay that creates a proton. This is one example of radioactive decay. Basically, if an electron hits one of these neutrons, it can become a proton. The other one is if we have an element and that decays because part of it breaks off into another nucleus. So you end up having an atom split into two different elements. So this is called alpha decay. This is actually what powers nuclear fusion, things like that, because when this happens, a little bit of energy is also released at the same time. The thing to emphasize is, especially in nature and natural processes, radioactive decay happens very, very slowly. And when it happens is completely random. There's a very small percentage of chance that it's going to happen at any given moment, but you can't really predict necessarily when it is due to quantum mechanics, basically. So the way we can measure, though, because, you have a bunch of atoms, you have statistically at any given moment something is going to happen. You can then measure the average time for half of all the atoms of one type to change into the other type. This is called the half-life of an element, or a given element. So as an example, if you start with rubidium-87, so 100% pure rubidium, and you wait 48.8 billion years, then you're going to have half of your rubidium. So the half-life of this particular element is much longer than the age of the universe, 48.8 billion years. Then you wait another 48.8 billion years, you're left with a quarter, another, you have an eighth, a 16th, etc. By the end of each half-life, what happens is half of the remaining atoms have turned into what are called the daughter elements. So in this case, rubidium changes into strontium-87 on the periodic table. So this is the very quick and dirty how radioactivity and how half-lives work. The important thing about radioactivity, though, is we can actually study this in labs, and we know quite a bit about how it works, thanks to the fact that you can actually go into laboratories on Earth, test different elements, figure out things like how the half-lives are. Then when you take a sample, you can take it into your lab and you can test it and measure it and figure out how much of a certain half-life there is, and therefore how old your material must be. The most famous one is probably carbon-16 dating. That only works for a few thousand years, but basically the idea that anything that is a more recent biological product, so if they find stuff in ice age encampment or something like that, they can usually go thanks to studying the radioactive decay of what is called carbon-14. That only works for a few thousand years, though, so instead we have to rely on other elements for half-life decay testing. But we can do it for other things. And so, for example, on Earth, we can date rocks, and the oldest dated rocks that we have on our planet are actually over 4 billion years old. The oldest rocks, it turns out, are up in northwestern Canada, up in the Yukon Territory, Northwest Territories, part of the Acasta gneiss deposit. One of the rocks here on the right is what that looks like. And we have basically figured out that those rocks are over 4 billion years old. But so that's our planet. How do we measure things from other planets? So the answer is we have rocks from other planets, thanks to meteorites, which have been coming down from space and pummeling our planet for years and years and years. And the oldest meteorites we have are over 4.5 billion years. It's like 4.50 something. We also have lunar samples, of course, because the Apollo astronauts went to the moon and brought back a significant amount of rocks. Fun fact, we actually have rocks from Earth that originated from Earth, and then they picked up on the moon and then brought back to Earth and dated. So we actually have 2 samples of Earth rocks, and not all from our planet. We also have meteorites from places like Mars. So basically, because we have Mars rovers and things like that now on Mars, we know the chemical composition of Mars very well. And then we have some rocks that have landed on Earth that we figured out have the same chemical composition as those Martian rocks. So we actually have pieces of Mars on Earth as well. We have some asteroids as well that we believe that some of our meteorites are from. And most of these will tell the same story. The idea that the solar system, or at least the rocks that are in the solar system, are about 4.5 billion years old. There's another thing we can do to figure out how old something is. And it has to do with craters. So craters happen when one of those meteorites hits the surface, leaves behind a giant hole. And you can basically figure out how old something is by counting craters. It's a rough proxy for how old a surface is. So I have 2 images here, one on the left, one on the right. They're both parts of the moon. And the question here is, which section of the moon shown above is older? Okay, I see a lot of B's, and you are right. So there's more craters. And that means that there's been more time for craters to hit that surface, right? So if you have a certain rate of craters all the time, then you're going to have a certain number hitting any surface. So if it's a younger surface, there just hasn't been enough time for craters to form. So with these 2 things in mind, we're going to now talk about various cosmic influences that happen on our planet Earth. So key characteristics of Earth. I think we've discussed most of these already in this class, but just as a primer, we define everything in the solar system in terms of Earth. So 1 mass of Earth, 1 radius of Earth is kind of our standard when we compare to other planets. Density, orbital period, 365 days, 0.25. That's why we need leap years. We are 1 astronomical unit from the sun, plus or minus a little bit. We rotate once a day, every 24 hours, and we have an orbital tilt about 23.4 degrees. So as I said, I think we've discussed most of this already in this course. So here's another question. So we have the Earth and we have the moon. If we're thinking about those craters, which objects should be hit by more asteroids per unit area? Okay, I'm seeing pretty much the same of A and B. I hate to say this, guys, the answer is C. So let's discuss why this is. Like, which object? It's not the same as which object has more craters. So if you just imagine there's space debris out there, all these meteors that are, in the line of fire of everything, there's actually statistically the same amount of stuff out there, and they're going to hit the same things. The trick about Earth is we have a younger surface than the moon. Most of the moon's surface has not really changed too much since roughly its formation. And our surface definitely has a lot of activity going on it. We're going to discuss that activity more. So it is, though, then a rough proxy, though, for it's not that there's more craters hitting the moon versus the Earth. It's just that we don't really see as much evidence of that. So we're going to dive now into detail on why exactly this is. So to remind you, at the end of last week, we discussed that the Earth formed as these little planetesimals collided and struck together, and they created a hot ball of molten rock called a protoplanet. The proto-Earth then differentiated, where the molten, so more dense material, basically like the iron, things like that, sank into the center and created what's the Earth's core today. And then we have less dense material that floated outward. And this is why we have layers in our interior. As the Earth then cooled, basically this structure got frozen into the Earth. And so we have our outer crust, we have our mantle, which is kind of this convection weird area, and then we have this liquid core in the center. And so I really like this comic, which is basically somebody reading about the Earth and then says, I freak out about 15 minutes into reading anything about the Earth's core when I suddenly realize it's right under me, which is true, but I'm also, the reason I'm pointing this out, so if we look here at the Earth's crust, this little bit, I mean, it is maximum 10 to 40 miles at any given point on our planet of our Earth. So it's much thinner in the oceans because of the type of plates there. So it's more like 10 miles. But out here, it's about 40 miles. So, I mean, 40 miles, that's like driving up to like Albany or Salem or something like that. So, like, it's really not that far until you start getting to these really molten areas. Like our crust is actually, we're on a very tenuous little bit compared to the size of the planet. So that's always just kind of one of these perspectives that crazy stuff starts happening when you start going down. It's just really hard to go down. That's why we, only have gone so far. So we just discussed that craters are rare on the surface. So let's have a little discussion. What keeps the crust smooth? Yes. Okay. So we have renewal going on. Somebody had their hand raised in the back. Yeah. Yep. Movement of the tectonic plates. That's a really, really big one. So yeah, we have basically the two primary answers here. So the first is erosion. So we have a lot of erosion on our planet caused by wind, water, and ice. So this is changing our surface over time. I'm sure you guys have all heard about erosion at some point before. And the other is lava flows. Lava flows and rock keeps getting recycled at the margins of our tectonic plates, and they can erase signs of craters from the surface. I should emphasize they erase signs of ancient craters on the Earth's surface. We actually do have a couple craters that we think are due to impacts on this planet. So probably the most famous one in the United States is called Meteor Crater, very creatively named, in Arizona. It was formed 50,000 years ago by a 160-foot wide meteor, and the crater's about a mile wide. So has anybody been here by chance? Yeah. What'd you think? Yeah. So I went when I was 15 years old. We went on a family trip to the Grand Canyon driving up from Phoenix. And I was already very into astronomy and heard about this. And it's like an hour out of your way from Flagstaff going east on the interstate to go there. And my family spent the entire hour out there making fun of me for wanting to go see a giant hole in the ground. And then on the entire hour on the way back, they just kept being like, oh, that was really cool. I'm glad we did that. So if you're ever doing a road trip in Arizona, it is actually very, very impressive, even though it just sounds like a giant hole in the ground. Another pretty famous crater. Oh, sorry, did you have a question? So they have pieces of it still. There's pieces. Yeah, so there's bits of it. We're going to keep talking about this. But I mean, we have meteorites, right, on our Earth. And yeah, people have dug around and they've found pieces of this. It's called the Barringer meteorite. And you can go into museums and see parts of it. Yeah. One meteorite we've never actually found, though, but we have ample evidence of is I don't know how, unfortunately, to pronounce this Chicxulub crater, which is in the Yucatan of Mexico. This is the most famous crater, obviously, to some people, because this is the one that killed off the dinosaurs when this impact happened 65 million years ago. It's about a 5-mile wide meteor, so, I mean, much more oomph. Basically wiped out any sort of, sunlight reaching our Earth's surface for many years. And the crater is about 93 miles wide. Has anybody here been to the Yucatan Peninsula of Mexico? No, yeah, a couple of you. Did you ever go see the cenotes when you were there? No? So if you go to the Yucatan, they have a lot of these caves, and they're called cenotes, and they're basically sinkholes. And so you can see that, I mean, it's a limestone environment. So you have these sinkholes. I mean, sinkholes happen in other limestone environments, but they have a very particular pattern. There's, first of all, a lot of them. So the ground is still pretty porous because of this giant impact all these years before. But you can also actually see the edge of where this impact happened. And this is actually, we've now realized based off the dating of what happened in this environment. I mean, there's been a lot of erosion over, the millions of years since it happens, but there's still evidence that this is where this giant asteroid hit that killed off the dinosaurs. So I actually took this picture some years ago. I went to the Yucatan, and it's actually very cool. You can go to the cenotes, and you can actually like go diving and stuff like that in them. Like you can jump off rope swings and even actually like explore them if you have a scuba diving license and stuff like that. There's thousands of them, and they're very, very interesting environments. You have some species that only happen in them, things like that. I'm also going to show you guys an example of a very new meteorite because you were asking what exactly happens to them. So in 2013, February 15, there was a very, very bright flash in the sky in Russia, in the area of the Urals called Chelyabinsk. So there's a lot of Russian dash cams, so we actually have quite a bit of footage when this happened. This meteorite, as it entered, it was brighter than the sun very, very briefly. I mean, you can go on YouTube and you'll see tons and tons of video of this thing. And we now believe that it was a 9,000-ton meteorite, roughly. It was coming in from the direction of the sun. Something comes in from the direction of the sun. We now have, surveys to look for all the asteroids that might kill us. No way to find it if it's coming in from the sun, though. Then you're pretty much, nothing you can do. But anyway, so it came in from that angle pretty early in the morning in Russia. And basically, as it was heating up in the atmosphere coming into Earth, it broke apart and exploded. And so I'm going to play this video. I warn you, there's going to be a bang if the sound is hooked up correctly. Come on. All right. I'm going to figure out the sound because it's pretty cool. Mic and audio. Oops. Oh. Yeah. So basically, there's a shock wave that was about 30 Hiroshimas of energy that happened when this thing exploded in the atmosphere, pretty high up, like, don't get me wrong. But then you can see, like, 33 million in property damage, basically because this shock wave broke all these windows in this surrounding region. And it caused about 1,500, okay, we can probably stop that. It caused about 1,500 injuries, mainly from that shattered glass that suddenly was going everywhere. So the very cool thing about this meteorite is if I can turn on the dock cam. Hello. Here we are. Is I actually have a piece of this meteorite. I have a little collection of curiosities at home. So here, this is a little piece of the meteorite. It exploded, but they managed, because, it was very well recorded, to figure out where some pieces of this fell. One big chunk of it fell into the middle of a lake, and, people then want to buy these things like me. So this is the piece of the meteorite here. I'm not going to pass it around because it's very, very small. But if you want to come up afterward to touch a rock that is 4.5 billion years old, but has been on this planet for less time than you, please come up and I'll be happy to let you have a little quick touch of it. And okay. Finally, not a crater. We have to mention this because we are very, very close to this crater. Crater Lake, Oregon. It's actually a volcanic caldera, about 7,700 years old. How many people made it up there? I'm sure a decent bit of this class. Yeah, if you haven't made it up there, it's a long day trip, but it's a really good day trip. You should do it. So we have all these craters on our surface. And then we also mentioned, though, we have this changing crust on top of that. So we're going to skip the activity because Amazon should not rule the universe, but they do. So we'll do that on Wednesday. So tectonic plates. The crust of our planet is separated into individual plates that are basically floating on top of that layer called the mantle. They kind of are jiggling around a little bit. They'll jostle, they'll move, things like that. So we are, where's my mouse? On the North American plate here, very close to the Pacific plate. The San Andreas Fault is running up here. And as we know, in Oregon, we are pretty close to this dividing line, and there's a lot of interesting things that happen as a result of that. The plates seem to only form if there's sufficient water in a planet's crust. This is just kind of one of those things. It turns out you need the water to be some sort of lubricant, or else you don't really have plate tectonics happening. So it's a good thing we are basically on a planet that's 70% water, because then we can have plate tectonics. The reason plate tectonics work is, as I said, we have this mantle layer, and there's this process in it called convection. Convection is the idea that if you have material, hot material rises, cools, and then sinks. So down at the core of the Earth, which is very, very hot, if you have the lower parts of the mantle, they heat up, and then, you've all heard hot air rises, cool air sinks, right? So the hot material will rise. As it rises, it starts to cool down, and then eventually it will sink back down again. So we have this convection loop happening. I mean, to be clear, this takes a very, very long process, like millions of years, to happen and things like that. And the tectonic plates that, as I said, are kind of just floating on the top of this layer, this very thin skin, are carried along the tops on these convective cells. What ends up happening then on our planet is we have geological activity. So you have various areas. There's things called rifts, hotspots, and subduction. So the rifting is what happens when you have seams that are opening through which magma slowly rises to build new rock. So rifts, so we have a very big rift near us, the Cascade Mountains. That's a good example of a rift. We also have hotspots. So as a plate moves over a hotspot in the mantle, volcanic chains form. So a hotspot is kind of like not moving relative to the plate. It's staying at the same point, and the plate is moving underneath it. So the Hawaiian Islands are a very, very good example of this, probably the most famous example. This is the most newest of all the Hawaiian Islands, and these are the older ones. And then you can actually, if you go, there's like one that's still 1,000 or 2,000 feet below, and it will eventually become another Hawaiian island. So basically, the Pacific plate is moving. The hotspot keeps creating new islands as it's moving. Finally, we have subduction, which can push up mountains as continental plates crunch together or build volcanoes. So as an example of rifting, in 2021, my husband and I went on what I'm calling our hooray, we're vaccinated trip, because it was like May of 21, so we could finally go somewhere. And we actually chose to go to Iceland. I was living on the East Coast at the time. And at the time in Iceland, they had a volcanic eruption called Fagradalsfjall. Anyway, they always have volcanoes in Iceland, but the thing about this volcano that was very unusual is it was actually pretty close to the populated part of, it was pretty close to the airport. Like you could see the smoke from this thing as you were landing at the airport in Iceland, and it was only about an hour's hike to go out to the viewpoint to see this volcano. So we did it, and I took a lot of videos and pictures, so we're going to look at this. So this is, maybe 2 miles or so from the volcano. And it was doing this roughly every 10 minutes, what I'm about to show you guys. So you see the lava is going outward. And then so keep in mind that's molten rock. So then you kind of see it and you realize it's rock, and then it's falling. And it's just like, wow, okay, that's an incredible amount of power. Also, when you saw that lava going out, you felt the heat even 2 miles away on your face. Like it was hot. And it was very cold that day. It was like windy and drizzling. And suddenly it was like, oh, nice and warm. And so that was probably one of the craziest things I've ever seen in life. The other thing, though, you should notice is, so, okay, there's this lava coming out of this. Iceland is, one of the places in the world where, you have a rift. It's growing because the Atlantic ridge is basically growing what's going apart there. And everything around here, you might have noticed it's smoking. And that's because this is basically all the lava from the lava field. And it's actually still hot. So the other thing that was fun about this lava field is it turns out the hiking path was just going by the edge of the lava field, and you could just walk up to it and nobody cared. So yeah, here's me. You can see the lava is still hot. This is compared to where the volcano is. And then you could actually sit there and watch it grow. And it sounded like glass. That actually did happen. So we did actually also pocket some of the rock, obviously not the lava ones, like the cooled down ones. And I was looking this weekend in my house and I was really sad I couldn't find them because the reason they're very unusual rocks is they actually feel really prickly if you hold one. And the reason is there's never been any erosion on this rock, right? There's never been any water, no wind. It's like literally like a month-old rock. And if it's never been exposed, it's not a smooth surface. You never realize like all of our rocks pretty much that you ever pick up are pretty smooth surfaces because of erosion. So, there is examples of rifting. They tend to be pretty extreme and things like that. You don't have to go all the way though to Iceland to see what a volcano looks like. We have a lot of very nice volcanoes, as I said, in Oregon. Ours are actually, I think I might have misspoken earlier, are due mainly to subduction. So we have our oceanic plate next to us, the Pacific plate, the Juan de Fuca plate is the smaller one, and the dense oceanic plate is sinking as the less dense continent or the more dense continent, less dense continental plate over the dense oceanic plate. And then basically that oceanic plate is melting, heating up, creates our volcanoes like Mount St. Helens is the most recent example, though Mount Hood in the late 1800s had an eruption. So in Oregon, that's probably our best bet for a volcanic eruption, for better or worse. Finally, we have what are called strike-slip faults. So the most famous case of this is a little south of us in California called the San Andreas fault. We have two plates that are kind of just have a lot of pressure on them. Over time, at some point, the two plates are going to slip as they're grinding together. And you will, there's parts of California where you can literally see the fault line. You can actually see a lot of fault lines in a lot of the earth where they don't exist anymore, but they're impossible to date unless you have an earthquake that happens when you see the slip. So it's kind of one of those random things. So I just explained this story very quickly. Why do we know that plate tectonics is a thing, and how do we know that there's evidence for it? So the first thing to point out is we have identical rock formations and fossils on distant continents. If you ever go hiking in the eastern Appalachian Mountains in the United States, it turns out the most similar mountain ranges to that are in Morocco and Scotland, because basically the Appalachians are the oldest mountain chain in the world, and those mountains are the same on the other side of the Atlantic, despite now being thousands of miles apart from each other. Because you can see they used to be basically aligned. You can also find weird fossils in weird places, like there's tropical fossils and tropical plants in Antarctica. So how would they be in Antarctica unless Antarctica maybe moved at some point? And then finally, the fit of the continents and the topography of the seafloor is very hard to explain without plate tectonics. Like, why does it look the way it does? It turns out if you think of a jigsaw puzzle that moved out over time, that's the best way to think about it. Okay, we have our Earth. And the reason we're also doing this class, this is not a geology class, this is an astronomy class. We can now then think about geology on other planets because we can study, as I said, our planet pretty well. So do other terrestrial worlds have these sorts of features? If you think about something like this, it's called comparative planetology. So you're using observed features on one planet to then compare to another planet, and then try to think of how common these processes are, try to understand what is causing the environment on the other planet based off of what you see on the first planet. So the answer to this question, we're going to delve a lot more into this class when we talk about the individual objects, but just as a teaser is yes. So this is a picture of the moon when you look up at night at the full moon. And a lot of you guys know there's a man in the moon. So the man in the moon is actually, I think it's something like this, like there's an eye here, kind of a mouth here, and nobody knows for sure. But anyway, what the features on the moon are, though, these dark regions are actually called mare or seas. And they're actually ancient lava plains that are about 4 billion years old. We also have cratering on the moon. So this is the most famous, largest crater on the moon called Tycho's crater. Tycho Brahe, he has a crater. So we have these features on our moon, which is, our closest world to us. We also see, actually, there's a lot of volcanoes on other planets. Venus has more volcanoes than anywhere else in the solar system. We've counted over 1,000 of them on the surface. There's still some low-level activity of volcanism on Venus today. We're not entirely certain how much, for reasons we'll discuss more when we discuss the planet Venus. Venus is also covered by clouds, so we don't actually have really good pictures of these volcanoes, but instead we have There was a probe in the 90s called Magellan that mapped Venus to very high precision. So this is a radar map of one of these volcanoes called Mont Mons. Mons just means mountain on another world in the solar system. So you can see here's the volcano, and here's your volcanic plain, similar to what we saw in that Iceland video, right in front of it. And finally, Mars. Mars has a lot of really interesting stuff going on. So first of all, so this is also radar data, altimeter data for the planet Mars taken by one of the Martian satellites. You see that, this looks very similar to an ocean. Like it's a nice smooth plate, maybe some features going on in the middle of it, like maybe some volcanism there. There are some craters, don't get me wrong. But then over here, you have some crazy stuff. So over here, Olympus Mons is the biggest mountain that we know of in our solar system. We'll discuss exactly why that is when we discuss Mars. And then you have this giant rift here, which is actually the size of the continental United States, called Valles Marineris. It is a giant canyon. It's in fact so big that if you took a helicopter and floated in the middle of it, unlike the Grand Canyon, you wouldn't see either side. That is how big and how deep that canyon is. So clearly a lot of activity happened at some point in Mars's past. We're going to discuss this a lot more. A lot of people are excited because they think this activity is an indicator that there could be life on Mars. We'll discuss that more as well. Earth's interior. So how do we know that the interior of the Earth is differentiated in the first place? I just gave you guys a nice story. And to tell you this, I am going to need 2 volunteers. Okay, so the first thing we could do is there's a type of wave called an S wave. So you jiggle it up and down. This is called an S wave. So the wave travels relatively slowly, but it's basically going back and forth in a sinusoidal motion. Okay, now if we could stop. The second type of wave is called a P wave. This is a little bit further. And it can travel much quicker than the S wave. And the other thing to say about it is that a sound wave is a very good example of what a P wave is actually like. With that, I am now giving you guys an example of a map of our planet. And the way this works is, imagine you have an earthquake here on the left side of Earth. You have observers all around the planet. There's these seismographs everywhere. You get pretty instantaneous data these days on anything. And you're going to notice that some people feel all the waves. So they feel both the S and the P waves. Some people are only detecting the P waves. So if the S waves cannot travel through fluids, which one of these do you think is correct for what the core's composition must be? Okay, I'm seeing a very disparate number of answers. The good news is most of you chose one where the answer is that the inner part is fluid. That is true because, as I said, that the S waves cannot travel through fluids. You see that the S waves are not reaching this side of the planet. So that tells us that if they can't travel through fluids, then they're being trapped somewhere out here. For the outer bit, we can't tell because we don't have enough information just from S waves and P waves alone. So a lot of the idea about plate tectonics, what exactly the mantle is, there's questions about how viscous that material is. We're not 100% certain. There was a crazy Russian thing where they tried to drill down into the Earth's surface to try to reach the mantle at what they thought was a thinner part of the core. They had to eventually stop because it got too hot. So we don't actually know for sure what exactly that innermost bit is like. So just to wrap up, today in this class, we talked about how we know the age of the solar system, how the mantle and convection derives plate tectonics, how the Earth's crust is shaped over time, and the layers of the Earth and how we know the size of their composition.